So I just want to repeat a couple of absolutely obvious things that you really already are completely familiar with, at least I hope. Coulomb's law. To begin with, we've understood the importance of Coulomb's law from last time's discussion, but let's just try to, write down exactly what we're talking about here. So what is Coulomb's law? Well, in its most simple stated form, you have 2 point charges. And the labeling I'm going to use is that there's going to be a source charge, S, at a point in space, which is given by a vector, R, S. Okay, and here again, 2 minutes to get used to my notations. I don't usually write vectors with a little arrow on top, because sometimes I write an R hat or that sort of thing. Too many things. If I write a kind of under wiggle on a letter, it means boldface, right? Like in a book. And if it's boldface, it's that it is not a scalar. And most obviously, in this case, it's going to be a vector. Later on, might have matrices. These are going to be also boldfaces. So that's what I mean with this thing here. This is the vector in our case, 3-dimensional space, determining the position of this source charge S, okay? Which carries a charge, I'll write it immediately here, it carries a charge QS, okay? And then we have a kind of test charge, QT, at a position RT. And there's a force essentially originating from the source, acting on the target. And this force is a vector. Okay, so this is a vector here, which is a force, which is a vector. Yeah? And I note it as the force acting on the target coming from the source. Okay, and Coulomb's law is the actual mathematical expression for this object. So what Coulomb's law tells you is that the force on the target from the source is equal to, first of all, the product of the charges. It is proportional to both the source and the target charge. And it is along the vector direction from the source to the target. Okay, but with a 1/r² dependence. And the way we can write this is r vector over r cubed. Okay, so this is 1/r². Now you're going to tell me it's 1/r³. No, it's not 1/r³ because it's r/r³, because we keep the vector. Okay, so very often in expressions, you'll want to use this form here. And there's a proportionality constant for pi epsilon 0. And then this epsilon 0 is the so-called permittivity of free space. And here is where your excitement for modern science can know absolutely no bounds, because you can read the little contextual information about this on the online notes. And here I'll just flash them because I'm not going to write this on the board. The value of this permittivity of free space is given by this quantity there. So, 8.854 farad per meter. And then there's this other constant appearing there, mu0, the vacuum permeability, which had all these values here. And what's really, really, really exciting about this particular mu0 here is that most of the textbooks, including Purcell-Morin on this, are now outdated. Because of increased accuracy in measurements, they have actually decided to change the fundamental system of units. And this mu0, which used to take an absolutely exact value of 4 pi times 10⁻⁷ henries per meter, is now essentially a floating value. It's changed. So there's one of the Poxt equations in Purcell-Morin which is wrong. Okay, so be careful with this. It's not going to come to bite you. I don't think it's going to change your life very much. However, if you do have a bit of brain space, it's kind of fun to look at how these things are being done. These are people, scientists working in commissions, committees, and debating for years and years how they should actually define things and which is a fundamental unit and not. So I've tried to give you a little guide about this, okay? But again, without emphasizing the importance of this too much, read this for fun. This is not exam material, okay? But that said, yeah, so there is a constant in front of Coulomb's law, which determines in our measuring systems, in our agreed conventions for various physical quantities, what this force is. Okay, so more simply, you can just say that this force here, you might prefer to write it in terms of unit vectors here. So there's the same constant here, Q source, Q target over 4 pi epsilon 0. But now what I'm going to write is a slightly simplified notation. So it's the hat vector RTS, okay, divided by RTS. Yeah, I can even make it simpler than that. Divided by R TS squared, okay, where R AB in general notation is by definition just RA minus RB. Okay, I'll just very often use this kind of convention here. Now, so this is certainly a core equation. Therefore, I will surround it with a very aesthetic, hopefully not clashing with the position, green rectangle. Okay, so this formula here is really something that you should absolutely know and control by heart. The notation of R hat means unit vector. So this thing here means unit vector. That is a vector which is in your system of measuring lengths has unit length. Okay, so R hat dot R hat is equal to 1. And the norm of the vector, of course, so if I write R ts is, of course, by definition, the norm of the vector RTS. Okay, so what we're doing here really is just reminding you what Coulomb's law is, which you already know, but also just setting some conventions for the notations. Is anything unclear about any of this? No. Yes? Very good. Okay. So we discussed then some further things. Okay, so we're going to make use of this Coulomb's law quite a lot. Of course, we can refer to it. Oh, maybe I should say in the notes also, I told you that I was giving like labels to the equations. And again, these labels are not really numbers; they're essentially either letters or symbols. So in this case here, it's Coulomb C little l. So that's equation CL in the note. In the notes, you've also got it hyperlinked for future reference if we so need it. And I'll try to kind of keep track of these references here so you can find your way. Okay, so that's the first obvious